Hello everyone, me Ameya, Kshitiz and Arya Arasan are going to present paper we studied as a part of the research-based learning activity of the course Numerical Methods and Computer Programming under the guidance of Dr. Abhishek Patange sir. The title of the paper is A Simple Modification of the Newton's Method to Achieve a Convergence of the Order 1 plus root 2. The authored by Trevor J. McDougall and Simon J. Wotherspoon. It is from the journal Applied Mathematics Letters, published by Elsevier, with a CITE score of 5.8 and impact factor of 3.848. The contents of the paper include the motivation of the paper, aim and objective, introduction, the method, convergence, comparison, examples, results, conclusion, and what we learned from this activity. The motivation of the paper. The paper includes a simple modification of the standard Newton-Raphson method for approximating the root of a univariate function. For the same number of function and derivative evaluations, the modified method converges faster, with the convergence order of the method being 1 plus root 2, which is approximately 2.414, compared to 2 for the standard Newton-Raphson method. Numerical examples demonstrate the faster convergence achieved with this modification of the Newton's method. This modified Newton-Raphson method is relatively simple and is robust, and it is more likely to converge to a solution than are either the higher order schemes or the standard Newton method itself. The aim of this method is to formulate a better alternative to the standard Newton-Raphson method by modifying it, and the objective of the method is to find a more efficient method of finding the roots of an univariate equation than the existing methods. Introduction. Newton's method for determining a root of a nonlinear equation has long been favored for its simplicity and fast rate of convergence. Using only the function and its first derivative, Newton's method iteratively produces a sequence of approximations that converge quadratically to a simple root. While number of rules with higher order convergence have long been known, these have the disadvantages of requiring higher order derivative. In this paper, the Newton's Raphson method's formula has been modified as R is equal to x naught minus f of x naught upon f dash of half of x naught plus r, where r is the root of the equation to be found iteratively and x naught is the initial guess. It is found by the predictor corrector rule of the form x naught is equal to x naught star is equal to x naught minus f of x naught upon f dash of x naught, and x1 is equal to x naught minus f of x naught upon f dash of half plus x naught star, where f dash of x naught represents the estimate of the derivative at x naught. The initial predictor step is just a Newton step based on the estimated derivative, while the corrector step is motivated by the implicit relation in 1. Subsequent iterations are done to find the root. Now, Kshitij will continue.
Thank you, Amey. Now let us understand the method discussed in this paper. The sketch of the modified Newton-Raphson method discussed here is shown in this diagram. The initial iteration to find x1 is standard Newton-Raphson method, but to find x2, the function's derivative is not evaluated at x1. Rather, an estimate of the derivative is reused to find the intermediate value x1 star, and the derivative is evaluated at half of x1 plus x1 star. This step to find intermediate value of x1 star is called the predictor step, while the step to find the next x, that is x2, is named the corrector step. Once the iteration is established, the general iteration takes the form of shown in equation 3a and 3b as shown here. The unusual feature of this scheme is that the interleaving of functions and derivative evaluations, that is, the function and derivative are evaluated at different points as seen in this figure. Initializing the iteration essentially requires two starting values, that are x0 and x0 star. Now we have two options for that. First is to derive x0 star by Newton's method, that is x0 star equal to x0 minus f of x0 divided by f dash x0, or the second method is to simply set x0 star equal to x0, in which case the corrector step in 2b for x1 reduces to Newton's method in this equation 2b. In practice, these two options are found to be equally effective, and hence only x0 star equal to x0 case will be considered in this paper. In summary, the general modification of Newton's method that is examined herein is given by: first we put x0 star equal to x0, then x1 is calculated using the modified derivative at x0 plus x0 star divided by 2, followed by, for k greater than 1, these are the general expressions. So what are the key features of this method? The key features are: first, the value of x2 is calculated from x1 using f of x1 and derivative evaluated at x1 plus x1 star by 2, because this is a more appropriate value of the derivative as compared to the one evaluated at x1 in the standard Newton-Raphson method. The second feature is the same value of derivative is reused in the next predictor step x3. The reuse of the derivative means the evaluation of starred values of x in equation 5a essentially come for free, which enables a more appropriate value of derivative to be used in the corrector step 5b. Now let us discuss the convergence of this method. First we write xi is equal to r plus epsilon I and xi star equal to r plus epsilon I star, where epsilon I and epsilon I star are the errors. Then using Taylor's expansion in equation 5 shows that these relations can be obtained using the Taylor's expansion, where alpha is equal to half of f double dash r divided by f dash r. Here the alpha is the rate of convergence. It is convenient to form a non-dimensional error measures using over tilde as epsilon naught tilde equal to alpha epsilon naught I tilde equal to alpha epsilon I, and epsilon I star tilde equal to alpha epsilon I star, so that the equation 6 becomes these equations. Now, when we examine the sequence of powers for successive steps, we see that the approximation converges faster than quadratic. We can see in equation 8, in these equations, that the powers of epsilon naught tilde and of 2 are 2, 5, 12, 29, 70, etc. And the successive ratios of this power is 2.5, that is 5 divided by 2 is 2.5, 12 divided by 5 is 2.4, 29 divided by 12 is 2.4167, and so on. So this ratio r of consecutive numbers in this sequence is seen to rapidly approach a fixed number, which is approximately 2.4142. The Taylor series calculations above show that the numbers ni in the sequence 9 are related by ni equal to 2ni minus 1 plus ni minus 2. Now, when we divide this equation 11 by ni minus 1 and we set the limit ni by ni minus 1 equal to ni minus 1 upon ni minus 2, which is equal to r, we see that r is a solution of the equation r equal to 2 plus 1 by r. So when we solve this equation, we get the result r as 1 plus root 2, which is approximately 2.4142. This same asymptotic ratio r of consecutive term is also found from the sequence powers 1, 3, 7. So these are the powers of the starred expression you can see here: 1, 3, 7, 17, 41, etc. Hence, we conclude that this modified Newton-Raphson method of solving for fx equal to 0 converges at the power r is equal to 1 plus root 2, which is approximately 2.4142. That is, epsilon I tilde converges to epsilon I minus 1 tilde raised to the power 1 plus root 2, and epsilon I tilde star also converges to epsilon I minus 1 tilde star raised to the power 1 plus root 2. By comparison, the standard Newton method converges quadratically, that is, for the power of 2. For example, after 4 full iterations of the standard Newton-Raphson method, the error is epsilon naught tilde raised to 16, whereas the error remaining in our modified method is epsilon 4 tilde equal to 2 raised to 5 epsilon naught raised to 29, which is significantly lower than epsilon naught tilde raised to 16. But both these cases require 4 evaluations and 4 derivative evaluation at this stage. Now I would request Arya to continue.
Thank you, Kshitij. So now we'll look at the comparison. The paper presented a brief comparison between the existing root finding methods and the new modified Newton-Raphson's method based on the efficiency index. The efficiency of the root finding methods are given by rate of convergence raised to 1 by number of evaluations in each iterations. So we can see that for a cubic convergence, using this formula gives an efficiency of 1.4422. The standard Newton-Raphson method has an efficiency of 2 raised to 0.5, which is approximately equal to 1.4142, whereas the modified Newton-Raphson method presented in this paper has an efficiency of about 1.55. The secant method has the highest efficiency of 1.61, but has a drawback. When approaching near to the root, there is a least significant bit noise which affects the denominator and is unavoidable. The LSB states whether the binary integer is odd or even, and fluctuation in its values causes errors in computation. Cow's sixth order method has an efficiency of 1.5651, but it also has a problem that it converges to a solution less often than the regular Newton method itself. Jarrett's fourth order method also faces similar problem to that of Cow's method. In this table, we can see the various methods and their efficiency, and the number of evaluations required in each step is also shown. So now we'll look at an example. Of the several tests conducted, the paper presented few simple examples for better comparison. Here we can see one of the example that was solved to compare different methods. N is the number of iterations while Nf is the total number of evaluations. F of x n plus 1 gives the value of the function at the evaluated root. It can be seen how the modified method proves more efficient as it uses less numbers of evaluation. So what were the results of this test? Measure of performance here is to note the number of function or the derivative evaluations needed to reduce the error of the initial guess by 30 orders of magnitude. The new method outperformed the standard Newton-Raphson and cubic convergence schemes. Outperformed 16 out of 18 cases in comparison with Wang's method. The evaluation of the derivative in the modified method at the midpoint between the most recent solution and a predictor value of the solution, that is not unlike Newton's method, is the reason why the method converges to a solution more often than does the standard Newton method. In the tests performed, sixth order convergence schemes outperformed the proposed method, but in 8 out of the 72 cases, the solution did not converge even after 50 iterations. Similarly, with Jarrett's fourth order scheme, 10 out of 36 cases did not converge. So the conclusion of this paper is that the method described in this paper offered an increased convergence at no additional computational cost, offers greater efficiency in terms of total function evaluation. Stopping criteria can be implemented halfway through a complete iteration, that is, after the start stage. Several other schemes require multiple evaluations to complete on one single iteration and cannot be stopped midway. Though having lesser efficiency than higher order schemes, it compensates itself by providing a robust method and a higher probability of convergence. So what did we learn? We learned what is the rate of convergence for root finding methods. We learned that the efficiency index is not the best criteria to compare different methods, and the computational time and probability of convergence matters equally. The importance of improvisation in the existing methodologies and its impact on a larger scale was brought into light through this paper. Thank you.